So hello everyone, this is the fourth lecture in the series of Pulse Digital and Circuit lecture series. And in the previous lecture we have discussed the working of the UJT, and now we are going to discuss the basic principle of Millar and the Bootstrap time-based generators. So basically here the question is, in the previous lecture we see here previous lecture we have discussed the UJT, and we have seen how that we can generate the time based signal by using the UJT. Then the question is, what is the need of this Millar and Bootstrap phenomena for generating this time based signals? So actually, see here there is a problem. Like here, what we were doing, we were observing the output voltage across the capacitor, and this capacitor was charging by the supply voltage through the resistance and by the time constant of RC. So this kind of the waveform we were getting at the output. At the output means the voltage across the capacitor that was appearing in the charging process. So this kind of the waveform we were getting by this circuitry. Now here we have a simple problem, like you can see in the initial lectures we have discussed that whenever we are trying to generate the time based signal, the linearity is very important. Means we want to generate the linear signal, this kind of the linear ideal signal we want to generate. But whenever we are generating the waveforms by using the capacitor, so all the time the charging equation of this capacitor is having the function of exponential. That already we have discussed, that voltage across the capacitor is the function of e to the power minus t by RC. So whenever the waveform will generate by this capacitor, it will be exponential. If we are considering for very small amount of time, that is TS, so in that maybe it is having some kind of the linearity, but still there will be some deviation from its original or from the actual sweep that we want, pure linearity or the pure linear signal that we want. So in this concern, basically these two phenomena is given, that is the Millar, one is the Millar and the another one is Bootstrap. So first we will discuss what is the Millar principle, and then further we will talk about the Bootstrap principle. So here the theory is given that you go through across it, and we are discussing the basic phenomena and the basic principle. So this is the circuit of simple charging capacitor. So this is the capacitor which is charging by the supply voltage through the resistance R. And we know that the charging equation of this capacitor, or the voltage across this capacitor, that is represented here, see, that is VC. So that VC will be simply, it is equal to the supply voltage, that is 1 minus of e to the power minus t by RC. In this manner this capacitor will charge, and by the current IC. Now see, what is the charging graph when we will plot this equation? So it will look like you can see, it will look like if we are taking T here and the voltage across capacitor VC, the voltage across capacitor, this VC. So if we are plotting this charging equation, so this is the maximum value and this is the charging nature of this. And if at the same time you are interested to plot the IC also, the current IC with respect to time in this capacitor, so it will have the exponential decay. This kind of the curve you will get for IC. So why it happens? Because as the capacitor charges, it ripples the supply, and that's why the downfall occurs in the charging, and that's why it moves towards the saturation, and this phenomena is turns into the exponential manner. Okay, so actually to resolve this issue, because when the charging is, as the charging or the voltage across this capacitor increases, the current through this capacitor decreases, because it opposes the charging by the supply voltage. So to resolve this issue, what we can do? So in the resolution or in the solution of this, there is another circuitry drawn here. Like, see, this is the capacitor supply voltage, the supply voltage, and this is the resistance. So it is the same circuit. The additional thing is that we have a fictitious voltage or a hypothetical voltage we are connecting in the series of this capacitor. And what we are assuming, this voltage will be equal to the voltage of the capacitor, but of opposite sign. Means the magnitude of the voltage across this capacitor, that is VC, and the magnitude of this voltage will be same at all the time whenever it is charging also. So this will also be increase or decrease, whatever is happening to the voltage of this capacitor, in the same manner it will behave, but it will have the opposite sign to this. So this is a fictitious voltage we are connecting in this. So by connecting this voltage, what advantage you are going to get? The advantage is simple. Whatever the voltage is coming across this capacitor, it will be get nullified by this voltage or this fictitious voltage. So what happened? So this capacitor, the current is not going to decrease through this capacitor, and it will charge in a linear manner. That is actually the basic requirement of generating a linear waveforms. Okay, so that is the basic phenomena of the Miller principle. That's why. So see this circuit, and here we have given some name also. So this point between X and Y, we have a capacitor, and between this Y and Z, we have connected a fictitious voltage that is variable, and it will vary according to this voltage of capacitor in opposite manner. Okay, so now this is the voltage, the same circuit I have drawn here also. Now see the circuit here, this X and Y, there is a capacitor that already here we have connected. X and Y, we have a capacitor. So in this circuit, X and Y, we have a capacitor. Through this resistance, we are charging this capacitor by this supply voltage, and between this Y and Z, we have a fictitious voltage. And in this circuit, we are assuming that this Z terminal is grounded. So as you are assuming that this Z terminal is grounded, so this is the reference point in this overall circuit, and all the voltages from input side, and if you will divide this circuit into two parts, that is, one is input section and another is output section, so all the voltages will be calculated with respect to this point, because we are assuming that Z is a reference voltage. Okay, now one more point is there. If we are assuming that this voltage V and the voltage across capacitor C will same at all the time, so you can see this voltage and this voltage will get nullified. So the potential of X and the potential of Z will be same. What does it mean? That potential of X will be same as potential of Z, and if you are writing that V X Z, so it will be 0. Getting the point? So it means that this X terminal is virtually grounded, and that's why we are dividing this circuit into two parts. So here this is the input part we are assuming, that is VI between X and Z. This is the input section, and this X and this Y and Z, this will be the output section, and a capacitor is connected between these two input section, that is C. So the brief circuit of this is given in this figure 5.11b, and this is the circuit of Miller integrator circuit. Now see, what is the circuit? The circuit is same as here we have a point X and point Z. So this is the input section. So we are marking as this is the input voltage here between X and Z. So through resistance this R, we are charging this capacitor. So this capacitor was bridge between this input section and output section. Okay, so up to this is the input section before this, and between Y and the terminal Z is grounded. So this Y and Z, this is the output section. And what is there? So the voltage V, this voltage V is basically, the voltage V will be basically will come to this side, this voltage V, and that is also the V naught of this circuit, because this is the output section. And this capacitor, as we have seen, X and between X and Y there is a capacitor C. So between this X and Y we will connect a capacitor. Now when we are saying, so this circuit, what is the relation between this input section and this output section? What is the relation? See, this X and Z are at the same potential because this X is a virtually grounded. So you can say that V, X and Z is equal to 0. So input voltage is 0, whereas what is the output voltage? Because this output voltage V, it is connected in this polarity. See here, this V is connected in the polarity of this minus and plus. So the same kind of we are the same, in the same manner we are connecting here also. Okay, so this minus and plus, so the V naught is basically equal to minus of V. So the circuit that is linking to this input port and this output port is basically, the input is 0 to this circuit and output is something negative in magnitude. So what kind of this circuit? This circuit is an amplifier which is having an infinite negative gain, because if there is nothing in the input, in spite of that you are generating some voltage. Suppose this is the positive voltage, so this will be amplifier with the positive infinite gain, but the output you are getting negative. So this is the amplifier with the infinite gain, and this circuit is basically represented as Millar integrator. Okay, so this is the basic philosophy of the Millar integrator. Means we will get a negative sweep with respect to time. We will get a negative sweep with respect to time at the output of this circuit, and that's why it is integrator. So you are applying a positive voltage or and you are getting a negative sweep at the output. Okay, but if suppose we want the positive sweep at the output, then what we have to do? For that, basically the another concept is given, that is called the bootstrap. So bootstrap is the same by the philosophy. The bootstrap is also the same thing as the Millar integrated circuit is, but the only difference is, in the circuit we are not going to take this Z point as a reference, but we are going to take this Y terminal as a reference, as a Y terminal as a reference. So what will happen? So if we will try to plot by using this circuit, so what kind of the circuit? So this the input signal up to this, there is a resistance, suppose this is R, so this is the resistance R, and is connected by the voltage V, connected by the voltage V, and this point is basically X. Okay, and now we are taking this Y as a reference. So between this X and Y there is a capacitor, so there is a capacitor C, and this Y terminal is grounded. Okay, so this is the input section of this circuit. Okay, and now this Y is basically grounded, so this output terminal will be between Z and Y. So the output terminal here, suppose we are considering this X here and we are increasing this also. Now we want to make a link between input and output, so there is some circuitry which is given by the link. So this is what the input section, and this is what the output section here I want to, this is the grounded, so this will be common to the output terminal also. And we are taking this point is basically the Z terminal, because we are taking the output between the Z and Y. So this is the point Y, X, Y, and now we are considering the output between Z and Y, so this point is common to here. So this is the voltage, output voltage, and what kind of the polarity will be here. You can see now the polarity of this output terminal will be changed. In the white negative terminal is connected to this, so negative, and this positive. So now here at the output section you are going to get a positive sweep as compared to this Miller integrated circuit. Okay, so we have plotted this thing in this PDF also, like in this manner. See, this is circuit that is given in the PDF, and this is what the circuit we have drawn. So simply this is the final connection of the circuit. So this is the Z terminal that is connected between this. Yes. So this is the circuitry that we are giving in the PDF. So here just I have plotted for you how this diagram is made by using the basic circuit. And now see, when this is your input section, so this is something input that you are providing. This is the input section, and this is what your output section. In the input, what the thing that you are applying now, once again you know the basically that Vx and Vz are at same potential. That this philosophy already we have discussed. So see, here the input is available at the X terminal and output is available at the Z terminal. It means that whatever the input you are going to apply here, the same output will come across this output terminal. It means that this is the circuit of suppose amplifier, but the gain of this circuit will be +1 only. Then only this input will appear at the output section. This input section multiplied by this gain, this will turns into the output voltage. So that's why, so this circuitry will be a amplifier with a positive gain. So this is the only difference between the Miller circuit and the bootstrap circuit. So this is the amplifier, so this is the bootstrap mechanism. So here what you are going to get, you will get a sweep of positive voltage. So if you are generating output voltage here, so this will be positive, you will get a positive sweep with respect to time. But as compared to this, in the Miller circuit you will have a negative sweep with respect to time. Okay, so that is the basic philosophy of the Miller integrated circuit in the bootstrap. Thank you.